The next thing that I want to be able to discuss is routers, how they work, what they're doing. I mentioned earlier that a router itself will choose maybe a different path to get its data from destination to destination, from point A to point B. But it's also very important that we remember, internally on our network, we use switches. Now what switches do is they connect segments of our network. So if I'm connected to our switch, I'm one segment of the network. And if your neighbor is connected to your switch, that neighbor is another segment of the network. And then when you're connected to the network, to that switch, you are also a segment of the network. You can all communicate to each other as you did in the peer-to-peer lab. But at that point, you cannot leave your network and go out to the internet. The only way that you can leave your network and go to another network, such as the internet, is you would have to have a router in place. So routers connect networks, and switches connect segments of a network. Routers will connect your dissimilar networks. Routers use layer 3 addressing, which is like your IP version 4, and also your TCP addressing. Okay, TCP is not necessarily an address, but it is usually more of just like our segments and our protocols. Okay. Routers determine the best path to get from A to B, which means that if there are, say, 12 different ways for us to get our data from Harrisburg to, say, Australia, the router will then determine what's the best path, which is the fastest path, maybe which is the path with the least amount of devices to go through, the path that has the least amount of congestion, which is how then our data could actually get from point A to point B out of order, which is why we would have to then use our sequencing numbers to put everything back in order. It's used, we actually at times will have to reroute our traffic to the best possible destination. Now if we take a look at the graphic here, this router, this gigantic beast over here on the left, this is like your commercial router you might see in, say, your ISP. The one here in the middle, okay, this is one of what we call an integrated services router. This one might do our voice, it might do our video, might do our data. We would see this in more of our commercial buildings. And then if we look over here on the far right, this is your standard home router, your Netgear router. You're actually going to take this type of router and actually program one of these towards the end of your curriculum in CNT120 in the wireless chapter, because this is your standard wireless type router. All these routers all perform one similar function. They connect dissimilar networks. They connect your local area network, say your house, to your ISP, which is considered the WAN, or the wide area network. It's also important to understand that your switches that we were working with earlier can do an ARP, which means that's a broadcast. And if I'm going to send information from one node to every node on the network, that's called a broadcast. And it is not a situation that we want to have happen. Broadcasts typically congest a network and slow it down. So routers will not broadcast. Could you imagine how bad it would be if a router was broadcasting on the internet? Everyone on the internet would have to stop talking. Your Netflix and your Amazon Video and your YouTube would all just cease to work because somebody was broadcasting on the internet. So obviously we can't have broadcasts happening over a router. So a router will never ever broadcast network. Routers do have the capability, however, to filter our data based on the type of transmission that's going through. Say maybe I don't want video coming in, I don't want telnet coming in, no file transfer protocol can come in. All of that can happen on or be filtered by our routers. Okay? So we can allow certain types of traffic to get through. Okay? It'll allow local and remote connectivity, which means our local area networks can have their conversations on a network as well as communicating outside of our network. We can use routers to monitor traffic. We can use routers to diagnose. Our routers have the ability, we can use our routers to diagnose because we have little protocols running on there that are called SMPs. SMNPs are simple network management protocols. We have different kinds of routers that are out there. Okay, you have your interior router, which is pretty much any router that's inside your local area network. Okay, and then the router that you connect to that will actually take you out, like this guy right here. So these are all technically interior routers, right? And then this guy here, he's right on the edge. He talks to, say, my Comcast or my Verizon router right here. So he's on the edge of my network, or what we call the border. And then same with this guy here. Okay. And then I have my exterior router, which would be my WAN routers. Okay. Your Comcast, your ISPs, they would be on those particular exterior routers. There's one thing that L routers will have as well, okay, and it's something called a routing table, and we'll get into that in just a moment. Routers internal today, similar to these guys in here, these interior routers, in many cases, these interior routers are being replaced by something called a layer 3 switch. Now, a layer 3 switch is very similar to a router in that internally, inside of our networks, they can actually connect network to network. But that would be called a layer 3 switch. Okay? So now let's just step back just a moment. Switch is typically a straight switch, what we call a non-smart switch or non-manageable switch, operate at layer 2 of the OSI reference model, which is the data link layer. The data link layer is specific to MAC addressing. Routers use IP addressing, which is layer 3 of the OSI reference model. So what all the engineers have done is said, well, wouldn't it be ideal if we had different networks inside of our building? So I have my administrative network, I have my sales network, I have my HR network, I have my accounting network, I have my staff network, I have my guest network. Because you want to be able to segment your network inside of your building to make it more efficient and more secure. So then somebody came up with an idea. Well, what if we took these networks and we made a switch, segment them, and then when they need to communicate with each other, we could let the switch manage that routing. So now we have a multi-layer switch. So it's no longer just a layer 2 switch, we have a layer 3 switch. So it can do internal routing. Well, so then we said, well, if we can do layer 3 switching, why don't we do layer 4 switching as well? Which means it allows us layer 4, 5, 6, and 7, or what we call the software layers. So what if we said, let's also do some, say, packet filtering, add some security level to our layer 4 switching, and hence the term layer 4 switching. As we move up through the layer 2, layer 3, layer 4 switching, we end up with a great deal more of complexity, and therefore we also end up with a lot more cost as well. Layer 3 and layer 4 switches, we speak about them in the CNT120 and 125 classes, but you will not be programming them until you get into your 200 level classes as part of the CNT networking degree. Okay? There's one thing that is held in all of our routers, and including our layer 3 switches, and it's called a routing table. Now, it says up here it's a database that maintains information about where hosts are located and the most efficient way for us to reach them. And really all it is a list kept on the router that displays or tells the routers where you're located. It doesn't tell you the exact address you're at. It tells you what neighborhood you live in, what network you reside on, what street you're on. Another way to look at it would be is if I live on Blueberry Street and my house is 22 Blueberry Street, in the world of networking, I can only talk to the people on Blueberry Street. If I want to talk to somebody on Mulberry Street, I have to have a router. So the router connects Blueberry and Mulberry. So if I have something addressed to 13 Mulberry Street, then my router will look at its list of addresses and say, oh, Mulberry Street? Yes, I know where that is, and it will transfer my data over to Mulberry Street. All of that is kept in a list. That list is called a table. This is what routers use to be able to transfer data from one network to another network. So in this case here, router A knows about all, okay? It doesn't know about any of these PCs over here. It knows what network they belong to. Mulberry Street's over here, Blueberry Street's over here, and believe it or not, this right here is also a street because they're routers, okay? So this might be, say, Walnut Street right here. Okay? It knows about these. It doesn't know about these guys. It just knows that what street they belong to, also what we call what network, LAN B. It knows its address. And that's what a routing table is. How do I learn about those addresses? Well, if there's only one way to get from point A to point B, I might as well just type it in. Here's where network A is. Here's where network B is. And I just type those into the table. But what if my network is so big that I have so many networks connected? Well, in that case, I'm going to have to use something called a dynamic route, which then uses rules to calculate who I'm connected to, where they are, and how I get to them. And sometimes I might say, okay, I've got all these different networks that I'm connected to, and in the likelihood that, say, I know about these 10 different networks, and the network I'm trying to get to, it's not in my list. Where do I go? Well, chances are the network you're trying to get to is probably out on the internet. So in that case there, it's going to be the gateway of last resort. Which brings me up to a really good term. If we take a look at what we've got going on here, okay, all these guys right here, let's say he's 192.168.100.10, and then the next guy is 11, the next guy is 12, and so on, okay? This router right here will probably be 192.168.100.1. That's his interface. The plug, every port gets an address. So his gateway, how does everybody plugged into switch A leave the network? Well, you leave through the gateway. It's kind of like your yard. Okay, you have a fenced-in yard. How do you leave your fenced-in yard? Well, you must go through the gateway. You must open up the gate and leave through the gate. That's how you leave the fenced-in yard. How do I leave my network? Through the gateway. Okay? If I don't know where to go, I'll use the gateway of last resort. Okay? How do I find out this information? How do I program it for one? Well, I would use the IP route command. Okay? If I want to view it, okay, on a Windows system, I would use the route print command. On a Cisco router, I do a show IP route command. And basically what it'll tell me is based on their operating system, it tells you about the networks it knows about. If I do a show IP route on my Cisco router, it'll tell me the routers I'm directly connected to. It'll give me the router's interface and with the L command. And then to go along with the route command, I have some other verbiage that I need to go through. Okay. What determines my path? Okay, and I was talking about this earlier on what determines the path for me to get from point A to point B. Okay, one, hop count. So what's a hop? Well, if I'm going from router A to router B to router C to router D to router E and so on, every new router is a hop. So I might look at my metrics and say, well, I've got 5 hops to go to here. That doesn't look too bad. I'll go this direction. Then I also might look at it and say, okay, this guy's plugged into a DSL line, and this guy's plugged into a fiber optic line. So in theory, okay, my bandwidth for my fiber is going to be much better than my DSL. I should go this way. But perhaps there's problems with my fiber optic line. Maybe I have some delay or latency. Delay is latency. Okay? Maybe there's just too much traffic on this line, so I'll choose a different path. All these things are called metrics, which will determine which path my router is going to take, which also lets us understand that not every path chosen is going to end up being the best path. Routers will change, in essence, change their minds as the transmission is occurring, due to the fact that the path that we originally had chosen became congested, or the path that we had originally chosen went down, and then the routers will then choose or change their choice of destination. Okay, next thing we want to talk about are the routing protocols. Now, if we take a step back to where we started our chapter, we have the routed protocols. That would be ROUTED, routed protocols. Routed protocols are used by the user. That would be something like TCP IP and, say, Apple Talk and NetBEUI and IPX SPX. Those are all what we call routed protocols. TCP IP being the one that is used today. Routing protocols are the protocols that the routers use, and that's what the routers use to communicate to other routers only. Routed protocols are what the user uses to be able to communicate with other nodes and devices. Routing protocols are what routers use to communicate to other routers, and thus allows them to build their routing tables. Routers rate the reliability of the routes and what route to use based on something called an administrative distance. So, for example, if I have a router that's directly connected to another router, it's got an administrative distance of 0 because we're directly connected. If I have a router that uses EIGRP as its routing protocol, and it learns about another router through the protocol EIGRP, which is the Enhanced Internet Gateway Routing Protocol, I'm going to have an administrative distance of 90. Now, the one with the lower number, that's the guy who's trusted the most. And all based on whatever routing protocol you're using. Say if you're going to use RIP, which is called the Routing Information Protocol, which strictly only uses hop counts, an older protocol. And routers only learn about the other routes every 30 seconds. So if a route would have gone down in those 30 seconds, we're not going to know about it. So that has an administrative distance of 120. So your trust factor goes based on what's called that administrative distance number. Now, the time it takes for us to know about the different routes that are going on is called our convergence time. Okay? And so, for example, if I broadcast out like right now that I'm connected to router B, and then 5 seconds from now, my connection to router B goes down. So everybody's trying to connect to router B through me, but they can't get to it because that link went down. That's going to be a problem with our convergence time. So, unreliable route. Now, all the extra stuff that's going on to make these network paths work, all the administrative distances, all the extra packets going out, all the communications, all the sequencing, all that is called overhead. Everything that happens above and beyond transmitting our data payload, that's called our overhead. Okay? So now if we take a look at our different types of protocols. RIP, that's one of the oldest protocols we got. It's an interior gateway protocol. Okay? It's called a distance vector. If it's a distance vector protocol, what that means is it strictly relies on hop count only. So it would say, well, this one here is 6 hops, and that path over there is 8 hops. I'm going to use 6. Boom, done. RIP version 2, same deal. Okay, it was just an enhanced version of RIP 1. Really, all it did is it kind of just improved on a number of the different problems or limitations that RIP itself had. Next is still used, it's used commonly today. It's called OSPF, which is our Open Shortest Path First protocol. Now it's a link state protocol. See, now what happens here is instead of just being connected to 2 routers or 3 routers directly connected to them, is it's connected to a whole bunch of routers that are programmed using the same protocol. And they're all linked together by a little something called an area. So I can have 20 routers in my area. So for example, let's say I'm looking at routing through half of Dauphin County, say Harrisburg City, okay? And so I have got 20 routers in Harrisburg City which are connecting me to the internet. And every one of those routers knows about each other. So because they're all linked to each other through cabling, through telecommunication cables all over the city, and they're all saying area 1. So what happens is, if one of those links goes down, a broadcast of through the routers using the routing protocols, broadcast goes out and they all draw a new map of how the network's supposed to look. Then if that route comes back up, that link comes back up, they all redraw. Now, this is a great protocol in that RIP broadcasts every 30 seconds, whereas the link states only broadcast when a link comes up or goes down. Okay. Another common one used was ISIS, and then the only protocol used for exterior would be the EGP or BGP, okay, which is an advanced distance vector protocol. And this is what I just talked about here, the interior gateway protocol, okay, used by interior routers and border routers. They would be either distance vector or link state. Okay. And the only EGP, exterior gateway protocol that I just mentioned used today is called border gateway protocol. Back to the same graphic we had before. Okay. These routers inside the clouds, okay, they could be using RIP, they could be using OSPF, they could be using ISIS. Doesn't really matter, because they're all interior gateway protocols. You're going to use whatever you want to use, okay? Whatever you feel is going to be the most efficient to make your network run as smooth as possible. And then the border routers are going to talk to the exterior router using BGP.